Bazen chatten bana yazıyorsunuz. Onları görmeyebilirim zamanında. Eğer hani sorunuz varsa beni doğrudan durdurabilirsiniz. Hocam ya şurayı anlamadık diye durdurup sorun o anda. Hani chatte yazdığınızı sonradan görüyorum. Ben gözümün önünde olsa da fark etmiyorum. O yüzden bana hani direkt durdurup sorabilirsiniz. Sorunuz var mı buraya kadar? Tamam. Eğer yoksa ben bu elektrik devresiyle ilgili bir başka model daha vereceğim. Fiziksel model. Aynı diferansiyel denkleme sahip. Ee, Buna biz ne demiştik? Example 1 demiştik. Example 2 diyeyim. Ee, Şöyle bu sefer elimizde so this time we have water flowing in a pipe. PT şey olsun the pressure of the water at time t. Suppose we have something like this. So water is coming from here, and we have something like a resistor. Maybe I should. Resistor is part of the pipe where you put, for example, some sand in it and so on, so that the water has difficulty passing through this part. Okay, so this is the resistor, and then here we will have a water tank. This will be, let's say, a cylindrical tank. Okay, cylindrical tank like this, and QT is the amount of water in the tank at time t. Okay, at time t, and PT is the actually PT is the pressure at the bottom of the tank. So this is the pressure of the water at time t at the bottom of the tank. Okay. Well, what is the pressure at the bottom of the tank? Suppose this is the height of the water. So this is the height of the water. Pressure is just, right, basically the height, right? Height of the water, HT, height. And what is that height? It is just the total amount of water divided by the cross-sectional area, right? AT, A, cross-sectional area. And this cross-sectional area here is just our capacity, actually. Okay, C, let's say C is the cross-sectional area. So water flow is like electric flow. QT is, in our case, the amount of water in the tank. PT is the pressure at the bottom of the tank, and that is nothing but the amount of water in the tank divided by the cross-sectional area. And what about the inductor? Inductor is, you may consider it this way, inductor. So there is a big wheel here, okay, big wheel. Okay, a heavy wheel, okay, rotating in both directions. And suppose this wheel has no what friction. There's no frictional force on this wheel. It just moves with the water, and if the speed of the water is not changing, of course that's nothing but the pressure difference between the two ends. If the pressure between the two ends are the same, then the water is flowing at a constant rate. And this wheel will rotate at a constant rate. And we assume that there is no loss of energy, there is no friction or anything. So this wheel will rotate at a constant rate. If the pressure uh, changes at one end, then of course water will try to move faster or slower uh, than it is its current velocity, and the wheel will resist to that, right? If this is a big wheel, heavy wheel, and if you push the water uh, so that it moves faster, of course this wheel will resist to that because its momentum will resist to that, right? It has a big mass, and if the water gets slower, then and the wheel will just push the water to the other side as a pump, like a pump, because it has a big momentum, so it will just take water on one hand and push it to the other hand. Yani buradaki bu tekerleği, büyük tekeri, bunu bir değirmenin çarkı gibi görebilirsiniz. Bunu inductor olarak görebiliriz. Okay? Inductor olarak görebiliriz. Dolayısıyla bu da bir RLC circuit. Rezistans borunun içindeki kum olarak görülebilir. Suyun akışını zorlaştırıyor. Inductor'ı büyük bir değirmen çarkı gibi görebilirsiniz. Su sabit hızla giderken hiçbir kuvvet uygulamıyor bu çark. Ama su hızlanmaya veya yavaşlamaya kalkarsa o zaman çarkın momentumu, kütlesi ona karşı koyacak. Bu ise su tankı. İçindeki suyun miktarına göre basıncı artacak veya azalacak. Peki toplam basınç nedir? Şuradaki basınça da diyelim biz, ET diyelim. So ET is the pressure. ET is the pressure, water pressure at the uh, uh, uh, beginning of the pipe. Of course, water moves in both directions, right? Water can move in this way or this way. Uh, well, the of course pressure here is the sum of the pressures, right? And what will happen? What will happen again? We will have the same kind of stuff. ET will be so this pressure here will be the pressure differences at the end of each circuit element. The pressure difference here, the pressure difference here, and the pressure difference here. And that's the, that will be what? So we are R, and IT is again the current. So the rate at which the water flows, the velocity of the flow, uh, the velocity of the water, and then we have this, okay, no, L times plus QT divided by C, or so this is L times Q double prime, because I is nothing but Q prime, so I prime is just Q double prime, and then I have R times Q prime plus O1 over C times Q. Okay, so again we have an RLC circuit, nothing but an RLC circuit. Okay. Any questions so far? Okay. What about linear and nonlinear equations? Let me talk about also on that, linear and nonlinear equations. Okay. If the equation involves no term which is in the form of product of dependent variables or their derivatives, then the equation is called a linear. Otherwise, so if there are terms which involve product of dependent variables or their derivatives with their derivatives, okay, so a dependent variable is multiplied with the derivative of itself or some other dependent variable, then we call the equation nonlinear. Otherwise, the equation is called nonlinear. Okay. Let's see some examples. All the examples we have seen above are linear, right? So let's say this RLC circuit, for example. Sorry. This is linear. A nonlinear equation has the following form. For example, suppose we have an equation like this. Y squared plus y prime equals 0. Here, a dependent variable, suppose y is a function of t, is multiplied with itself. Therefore, this is a nonlinear equation, is nonlinear, okay? Because it has a term uh, where a dependent variable is multiplied with itself. This equation, let's say, is also nonlinear. Again, a dependent variable is multiplied with its derivative, right? Here again, I assume that y is the dependent variable and t is the independent variable, and y is a function of t, okay? So this is also non-linear equation. Or we may have something like this. Let's say ux x plus ux times uy plus 2u equals, let's say, x times y. Here, u is a function of two variables and it involves derivatives with respect to more than one variable, x and y. So this is a partial differential equation. Highest order derivative term is the second derivative term, this term. Therefore, this is the second order partial differential equation. And it involves a term where two derivative terms are in product form. Therefore, this is a nonlinear term, nonlinear term. Therefore, this is a nonlinear equation. So, this is a second order because the highest order derivative term is this one and the order of the derivative is 2, okay? Second order nonlinear partial differential equation, okay? All right. As in the case of algebraic equations, remember that in linear algebra you have seen linear systems, right? Linear equations, and they're relatively easy to solve. We have a very established, well-established theory for linear equations. We understand them and we know how to solve them. But nonlinear equations, we have almost no idea how to solve them. We don't have formulas for the solutions and so on. For example, for algebraic equations, for quadratic equations, we have quadratic formula. For third and fourth degree algebraic equations, polynomial equations, we have some formulas giving us the solutions. But if the degree of the polynomial equation is larger than or equal to 5, then we don't have even a formula for the roots of the polynomial. So the nature of algebraic equations, of degree larger than 1, nonlinear equations are uh, very difficult. We don't have a nice theory. So the same thing uh, applies to differential equations. Linear equations, we understand them. We have a well-established theory. For nonlinear equations like this one, things are very complicated and we don't have, a well-established general theory. We have theories for specific equations, but if you pass to a different nonlinear equation, then that theory will not help you. Okay. So as in the case of algebraic equations, linear differential equations have a well-established, general theory. However, for nonlinear equations, nonlinear differential equations, we don't have a general theory. I mean, we have a theory, but it is not, as understood as linear ones theory. Usually, we have theories for specific equations, and that theory doesn't apply to another nonlinear equation. Okay, for each nonlinear equation, you have to build up a different theory. Okay, that's why uh, life in the nonlinear world is very difficult. Okay, all right. Let's talk about uh, linear equations a little bit more. Uh, and nth order linear ordinary differential equation has the uh, following form. But it's an ordinary differential equation. Uh, we have only one independent variable, because derivative terms doesn't involve uh, derivatives with respect to more than one variable. So for simplicity, let's assume that we have one dependent and one independent variable. So here t is the independent variable, and y is the dependent variable. Uh, order is nth order equation. So we may have derivatives first order, second order, third order, up to nth order. And we know that no two dependent variables, so no two y terms or their derivatives, will be in product form. So this means what? I may have nth derivative of y, but this will not be multiplied with any other y term. So the coefficient of this could be a function of time, but that's it. Okay? And then another, possibly a function of t times n minus first derivative, and it will go like this up to let's say n minus first, so here first derivative, right? The sum of this index and the order of the derivative is added up to n each time, and then I will have a n t zeroth derivative. Zeroth derivative means no derivative, right? No derivative. And this whole thing could be equal to some other uh, function of t. So the general form of nth order linear ordinary differential equation is this. Here, uh, this a0, a1, an, and gt are coefficient functions. Okay. Let me also give examples of partial differential equations. We'll see later toward the end of the semester so-called the heat equation. So what's this? Suppose you have some, let's say, a metal object, okay, of length L. So this is x equals 0, x equals L. And at a point here, let's say uxt is the temperature at x at time t. So the temperature at this point at time t is denoted with this function uxt. Then this function obeys a differential equation. Then uxt obeys so-called the heat equation. And what's that equation? It is this one. Some constant times the second derivative of u with respect to x is equal to first derivative of u with respect to t. Okay, so this is a second order partial differential equation, and you see no two u terms are in product form, so it's a linear equation. This is a linear second order partial differential equation. And similarly, we have so-called wave equation. Sorry, wave equation. Okay, suppose we have some string. Okay, and this string, you pull it and then release it. It will, swing like this. Okay, and this is again, suppose it has length L, and at the point X you measure the displacement from the equilibrium. Okay, so uxt, the amount of displacement at x at time t. Yani bu x noktasında ve t anında telin denge durumundan ne kadar ayrıldığını gösteriyor uxt. Then uxt obeys so-called the wave equation. And what is that? Some constant again. Here also we have some constant. This constant is called diffusivity constant. It depends on the material the object is made of, okay? And also the surrounding. And here A is also a constant which depends on the material the string is made of. So this is very similar to the heat equation. The only difference is that the time derivative is also second order. Sorry. Okay, here time derivative was first order, but here it's also second order. Okay, and this is again a second order linear partial differential equation. Okay. Okay. Let me talk about linear first order equations. Method of integrating factors. So we will consider first order linear equations. First order means I have only first order derivative terms. Here, let's say, of course, well, in this course, we will mainly deal with ordinary differential equations. At the end of the semester, we will see partial differential equations. So, till the end, we will only consider ordinary differential equations. So we have only one independent variable, let's say t, and sometimes it will be x. Since it is first order, I have something like this, dy dt. And since it is linear, the derivative term is not multiplied with itself or with y. Actually, I should here, okay, we have stated the general form was this, right? So I have only first derivatives. So I have a1t, y prime t, a0 t, yt, and that's equal to gt. But we will write it not in this form. We will write it like this: y prime plus pty equals qt. Okay, so I just divide everything by a1t. So this is the equation we will try to solve. Okay. Well, let's see how we can solve this. Okay. Okay. Okay. Let me. Let me start with an example. Or okay. Okay. Yeah. Let me do it this way. We so integrating factor. Let me say integrating factor. What's an integrating factor? Remember the examples I have given at the beginning of the lecture today. We wrote the equation usually in this form: d over dt of something equals something, right here. And then we integrated both sides. So I will try to obtain this kind of form. Okay. Here, of course, this part y prime plus pty doesn't have to be derivative of something, right? Doesn't have to be derivative of something. But we can try to, uh, you know, change this equation so that the left hand side becomes the derivative of something. And the way we change this uh, will be by multiplying this thing with a function of time. So let me write it this way. Let's try to find a function mu of t, which will be called an integrating factor, so that uh, once we multiply the equation by mu t, the left hand side becomes the derivative of something. Okay, so I have this equation and I multiply this by some function. Okay, and this becomes, so I multiply this by mu, and I hope that this thing becomes the derivative of something, and that something is the following. I want this to be the derivative of mu times y. Okay, so we are looking for a function so that derivative of mu times y, y is equal to this gadget. Well, this means what? This means the following. So when I take the derivative of this, we get mu prime y plus mu times y prime. So this has to be what? This has to be mu times y prime plus mu y and p. And from this, what we see is that this term is cancelled with this, and what we end up is the following. So we get here mu prime times y is equal to mu times y times p, and this gives us what? You see, mu is the function of t also. Mu prime is just the derivative, so I have d mu over dt, and y's are gone also. Y's are gone. So I have this. Okay. In other words, we have d over dt of logarithm mu t equal to pt. All right. And from this, we see what? We see that ln mu t is equal to e to the power, sorry, integral of pt dt. So antiderivative of p. Therefore, mu t is just, or absolute value of mu t is just e to the power pt dt. And from this, we see that mu t is just plus minus e to the power pt dt. So we see that actually finding such a function is possible, and that function is just e to the power integral of pt, and you put any sign you want here, plus or minus. So given this equation, first order linear equation, ordinary differential equation, I can find this function mu t, so that when I multiply that equation with this mu t, I obtain an equation so that the left hand side is the derivative of some function. And once you have this, of course, once you have this, by just integrating, you will be able to obtain y. Okay? So that's the important thing. Uh, so note that uh, using mu equals mu t, we obtain which equation? We obtain this equation. So my equation becomes this: d over dt mu times y equals mu times q, right? Mu times q, and taking integral of both sides, mu times y equals integral of mu t qt dt, and from this we obtain what? We obtain y 1 over q time mu times integral of mu t qt dt. And mu was what? Mu was e to the power integral of pt. Well, which one should I take, plus or minus? It doesn't matter. All I want is just one integrating factor. So why not choose the plus one? So choosing the plus one, 1 over e to the power pt. So that becomes e to the power minus pt dt times integral mu t, which is e to the power pt, sorry, dt times qt dt. Okay, so that's the solution of the differential equation. Here mu t which is e to the power pt dt is called an integrating factor. We will see why we call this an integrating factor. Actually, we have seen already that, I can take this one or it's negative. They are both integrating factors. We have many integrating factors, and this is one of them. It's called an integrating factor. of the for the linear equation. Okay. All right. Let's see one quick example. So, okay. Solve the equation. Uh, dy dt plus 1 over t 1 over 2 times y equals 1 over 2 e to the power 3 over t over 3. This is a linear first order equation. Pt is just 1 over 2, constant function 1 over 2, and Qt is the function e to the power 3 over 2 divided by 2. Well, we find our integrating factor. Integrating factor mu t, and what was that? I can take, for example, this thing. So integral of 1 over 2, which is just t over 2 plus sc, right? Integral of this. And you see, any choice of c will give you one integrating factor. But all I need is just a single one. Therefore, I can give any value I want to c. And to get, to make life simpler, we just choose c to be 0 so that we get something simple. Just let c equals 0, right? Each choice of c will give you another an integrating factor. Okay, so we have many integrating factors. So our integrating factor is just e to the power t over 2. And then we do what? We multiply our equation, multiply the equation by the integrating factor to get what? E to the power t over 2 times y prime, right here I have y prime, plus e to the power t over 2 times 1 over 2 times y, and e to the power t over 2 times 1 over 2 times e to the power 3 over 2. So I just multiply the whole equation with e to the power t over 2 and obtain this. And I know that the left hand side is just the derivative of the integrating factor times y. And here I have what is this? 5 over 6t, I guess, right? Let's check if we did it correctly. When you take the derivative of this, you get y prime times this plus y times the derivative of this, which is 1 over 2 times e to the power t over 2. You have to do this so that you check what you have done previously, right? This is the checkpoint to avoid any mistakes you have done so far, okay? And then we do what? We integrate both sides and we get e to the power t over 2 times y, right? I have derivative of this and then I take antiderivative, so I get this, and that's the integral of this gadget. What is the integral of this gadget? So it is 6 over 5 e to the power 5t over 6 plus a constant, okay? And from this we get what? Yt is equal to what? I divide both sides by the integrating factor, and we get 1 over, okay, so this is just 3 over 10, I guess. No, 3 over 5. E to the power 5t over 6 plus c times e to the power t over 2. And what is the c? C is an integrating factor, so it's any real number. Yes. Okay. So this is the solution I have obtained. We will see later that this is the list of, evet. Öyle mi? Nerede? İnteg böleceğiz. Ha, şurası eksi olacak. Burada burada da eksi olacak. Tamam, haklısın. Çok teşekkürler. Evet, evet. Şurada da çıkartacağım onu. Yine burası t bölü 6 mı olacak? Yok, t bölü 3 olacak. Evet. T bölü 3. Tamamdır. Şimdi oldu değil mi? Evet. Tamam. So next time, or yeah, I mean tomorrow, maybe Wednesday, we will see that actually this is the list of all solutions. Okay. Uh, I have obtained uh, some solutions, but it is not clear at all that this is the list of all solutions. Maybe somebody else may come and obtain solutions which are not listed here, right? We don't know that yet, but we will see later that actually this is the list of all solutions. Okay, and we will see it later. All right, let me stop at this point.